To this hybrid seminar, and very good to see people.
Você não tem nenhum contato chamado terminal SP. Ok. Você quer buscar os dados de contato de quem?
Hold on, I'll just.
No, just close.
Okay.
Go ahead.
Didn't like me, right? So, as I was going, it's great to see people joining the seminar in person. And as I said, that it is being held in hybrid mode. So it gives me great pleasure to announce that Professor Gomes from Brazil is here with us. Just a brief introduction about Professor Gomes. So his full name is Anderson Stephens Leonardes Gomes. He was born in Recife, Pernambuco. So he completed his graduation and master's in physics from the physics department of Universidade Federal of Pernambuco, where he is presently a professor. His doctorate was in laser physics, obtained at the Imperial College of Science and Technology and Medicine in 1986, followed by a postdoctoral stint at Brown University in USA. He is presently a professor of physics, as I mentioned before, at the physics department of the same institute that he completed his graduation in. His scientific activities are in many areas, to be specific in the areas of laser applications and nano and biophotonics, nonlinear optics, and nonlinear photonic devices. He has co-authored more than 300 scientific publications, most of them very high profile, having H-index of 48. He has supervised 39 master's dissertations and 20 doctoral theses and still going very strong. He holds a very prestigious CNPq fellowship at the highest level, which is one of the very older ones and very honorable ones in Brazil. He's a fellow of Optica, the former Optical Society of America, where he was president of the International Council. He's also a member of the Brazilian Physics Society, SPIE, and the Brazilian Academy of the Progress of Sciences. He was associate editor of Advances in Optics and Photonics, and is currently associate editor of Light, Science and Applications, the Nature Group. There's a journal from the Nature Group. In 2010, he was Secretary of State for Science, Technology and Environment of Pernambuco, and was also Secretary of State for Education of Pernambuco from January 11 to December 2012. On the national level, he is a member of the Council of National Brazilian Fund for Development of Science and Technology. This is a federal government committee responsible for budget from the National Fund to Brazilian institutions for science and technology research. So you can understand that not only is a very prolific scientist, but he is one of those people deciding about what funds to be distributed to whom. So with this, again, we are really very pleased to have Professor Gomes out here. So Professor Gomes, over to you.
Well, thank you very much to all of you for being here, Professor Ganguly and all that have been with me last couple of days. Particularly interacting with the students has been very learned a lot because I'm at the physics department and here I'm at the chemistry. And nowadays we have this multidisciplinary approach, and that's where we learn a lot. So before my talk, I'd like to spend a few minutes. I'm here I was supposed to be here in January. There was that meeting in January. At last minute, we had to change. It was only online, but I already had the ticket. So I said, okay, I'll keep it. Next opportunity, I'll go. So I think this is my fourth time, or fifth perhaps, in India. For sure, the third time at IIT. Last one, I came as an OSA traveler lecturer. We saw the children's chapter in physics. So it was very good. I'm already planning to come back this year because I have the visa is for 1 year. So as long as I have visa, I keep coming back. So the Ministry of Science and Technology, we have in Brazil, in the last 3 to 4 years, they decided that photonics is strategic. So as we say, better later than never. So now photonics is being seen as something very important, and then that means we can have a resource, not as much as we wanted. And they also understand that we can have from that, we can have a convergence, not only of photonics, which is an enabling technology, but also its biology, nanomedicine, and so on. So what the idea is that the organizational mission is such that we have to combine knowledge, wealth generation, and improvement of the population quality of life. That's the new way of looking at things. And then from that, we can do lots of different things. I'm not going to go into all details. Certainly, you all know about this. So this is some bureaucratic details, which I can also escape. There is a lot of input for entrepreneurship. So nowadays you can be in academy, but you can also think of other approach, and entrepreneurship is one of them. So there is a particularly part of this Ministry of Science and Technology that is a department responsible for kind of transferring or helping to transfer this technology. As I have seen here, a very good example yesterday with your very nice microscope, phase microscope. So in photonics, we have some materials, some studies, and it became this national strategy until this year that we prepare another few years strategy. So there is an action plan, and this is divided in few points. One of them is encourage the process of implementing regional ecosystem. So they are spreading around Brazil. You see a map later. Identify the national technical capacity, promotion of human resource training. This is certainly the most important thing, and strengthening the international collaboration. So that's why one of the reasons I am here. So we have what we call a committee on photonics. This is a national committee. I'm part of this committee as coordinator of this, the National Institute of Photonics. We have a Brazilian Photonics initiative. So there are targets. It's time that we should do. Those targets, they go around these sectors and technologies. So we go from different sectors like communication, health, and then we have technologies. And then here we have the university institutes and groups that have the capability of helping in those in this matrix. So it is divided such it covers everything. So if you want, for instance, to something about mobility in optical communication system, then you have you can find that several of those institutions can work on that. So this is set up there. There are more on this one, and then this is concretized in this so-called CISPhoton, which is a system for photonics in Brazil. So they made a call for proposal. This is a map of Brazil, and they gave money to 10 institutions. You can see that most of them are in the south of Brazil. So above this line here, we have the northeast of Brazil and north. This is our group. We are the only one here. So we have to work for everybody. And then there are several labs. They go from, I like this one, from agri-photonics, which is photonics for agriculture, all the way to anything that you want. There are more. We have all the addresses. There is if you go into this website, you can see on YouTube a movie about every one of the 10 labs. We have some studies, as I said, already published, some mapping. This is about celebration of a Day of Light. There are some more material. And then this ecosystem, as I mentioned. And this ecosystem, we have also the so-called Institute of Science and Technology. This is a very, very big program in Brazil. This is for all areas of knowledge. There are about 100 institutes, actually 102 institutes. So there are 4 specific in photonics. This is the one I coordinate. I'll talk a little bit more about it. That's National Institute of Photonics. There are another 4 here, all of them in the south or southeast. As I said, they have all areas of knowledge: agriculture, energy, engineering, IT, and so on and so forth. These are the number of production publications and so on. There are these national manufacturers. We don't have many industry, particularly Brazilian ones, but there are small companies, and then of course many international companies that have the part of them working there, but main development is made outside. These are some numbers for marketing in Brazil. We have a nice international cooperation, particularly within the BRICS. Again, that's one of the reasons I'm here. At the end, I'm going to show we have our meeting, 4th meeting is going to be in Recife. So there is this so-called BRICS, Virtual Institute of Photonics. I don't know if you know about it. You should just put in this name. You find out what's going on, and where there are call for proposals and so on. So we are one of the members, leader members. At this moment, this Virtual Institute of Photonics is setting up a roadmap. So I'm in charge of part of this, and there are other players in Brazil and also abroad. So these are the institutes that I mentioned that are National Institutes and Photonics. Here, again, numbers. I escaped this, don't need this. Now, I'd like to end this part with this view graph. So we're going to have, I know it's a very short notice, the Ministry of Science and Technology has sent about a month ago a note everywhere. We're going to have the 4th meeting on the BRICS group of photonics, working group of photonics. It's going to be in Recife in August, 3 to 5. So if it's possible, someone from here would be very nice. It's going to be hybrid, so you're going to get all the information. So you cannot see this part, but there's a nice heavy program for the 3 days. So this is something we can talk more later if you are interested. So with this, I kind of end this part, and let's move on to my main talk today. I hope that I am able to, in the next 45 or 50 minutes, to give you a broad overview of what we are doing in Recife. And then this is kind of exemplify what's being done in other parts of Brazil. If we think of collaboration, going to Brazil, you should not stay in one place. You should take the opportunity to move around a little bit, know other people, know other labs, and of course, spend most of the time in my lab. So I'm going to give you a really kind of broad overview. I'm going to talk about everything from random lasers to nonlinear optics in 2D materials and to imaging by optical coherence tomography. I will concentrate more on this last part, and you understand why. I anticipate, I give you a spoiler, as they say. When the Nobel Prize was announced in physics, was announced last year, this colleague of mine said, did you read when they announced it, they launched a scientific document explaining why it was given to those guys. He said, did you read this thing? I said, no. He said, have a look. I looked, and there is a big part, I'll show you here, where they not only mention our work, but they show that our work, I didn't know that, our work connects 2 of the Nobel Prize. So this is, I'm getting close. I'm already in the reference for the Nobel Prize. So maybe next time I'm not in the reference, I'll be on the author list. I'll be happy. I'll come back here. Anyway, so this is how I come. So from Recife, which is here, I go to São Paulo. That's 3 hours flight, and then São Paulo to Doha, in Qatar. That's 14 hours flight, and another 4 hours to Delhi. Another 3-4 hours or maybe 6 hours airport, so not too bad. So once here, I'm going from here, as I said, I'm going to Mumbai, then to Chandigarh, to Roorkee, and then Delhi, and then back home. So in this talk, I will briefly talk about the National Institute of Photonics, and then our activities in our lab, which is called Labfoton, Laboratory for Photonics and Biophotonics. Then at the end, I'll discuss future work. Okay, so this is our campus, main part of the campus. Our department is to the right of this picture here. This is our National Institute of Photonics. It has 21 institutions aggregated throughout Brazil. We call 5 are consolidated groups, 5 are emerging groups, and we have what we call associated groups. These are like 2 or 3 people that are associated with us. So this is the full list here, about 63 researchers, and then about 150 students and postdocs. So these are permanent, and then the students and postdocs, they kind of move around. So remember I showed you this map where we have this Brazilian system of photonics. So what's interesting is half of these belong to our institute. So we kind of have, when I noticed that, because this one started several years ago, whereas this one started last year. So that means our institute is really important and congregate half of the Brazilian community in photonics for that matter. So what we do, we have in our institute 50 sub-projects in nonlinear photonics, device and applications, biophotonics and optical microfluidics. We have a very good international collaboration with several countries. We don't have any collaboration in South Africa, but we should do something like this. So just to give you some examples, this is from our group. In Russia, we collaborate with MEFI, working on nonlinear photoacoustic response of some nanomaterials. Here in 2018, I believe, yes, 2018, I was here for a conference, and then I visited Calcutta, this institute for, what's it called? Indian Association for the Cultivation of Science. First time I saw this name, I really loved it because, cultivation of science, it's something very, very important from the very, very beginning. So I gave this lecture there, and I was also glad to see Raman spectrograph. So everybody that works with Raman. So this picture is very nice, and I also was properly dressed. So when I visited there, I met this guy, Abhishek. Abhishek went to Brazil for 2 years. He had to come back to get married. And then, yeah, crazy guy. Anyway, no, important, that's important. So but he's going to spend another 6 months. He set up the whole photoacoustic system. Everything you see, set up, he did everything. I have another colleague there, Cid Araújo. He collaborated with Amitabh Patra for several years. So we have, I'm not there, but in that paper, but there are publications. I also have collaboration in China, and here we have used some nanoparticles they have developed there to do nanothermometry and apply this to dentistry. So I'm not going to go into detail, but this is a kind of very nice work. Also on Raman laser, random fiber lasers, again in China with Xenon 1. Okay, what about our lab? We work with biophotonics, nanophotonics, nonlinear optics, photonics device, and we also develop some educational activities. That's mainly training teachers to use technology. We have a lab with things like you have here, nothing special. We also have things for biophotonics, optical coherence tomography and microscopes and so on. That's me pretending to work there just for the picture. Our group in 2017, that's one of the last pictures together. And then came people start to move around. So now we have an individual picture. So this is we have a lot of collaborators. So you know, Paras Prasad has been here recently. Roman Kashyap is someone that left India many years ago, but he comes back quite often. And then this is the students and postdocs last year. And then most of them are in dentistry. So I strongly work with, you'll see why. Okay, money is from CAPES and PQ, all Brazilian agents, and then I also have some support from Air Force in the US and the Naval Research Lab. Okay, I'm not going to talk about this photonics device, but we have a facility for femtosecond writing. So as long as you have a femtosecond with high power, you can have this facility. It's very easy. But this kind of work I did recently, I kind of like it. I thought I would be rich because what we did, we encoded the QR code on a little piece of diamond. And I said, okay, everybody wants that, and then I'll be rich, right? But no, it's still there, just the paper. As I said, we use educational activities, exploiting technologies as pedagogical tools. So technology is not the end. Technology is enabling technology, is enabling, and in that case, this is to teach, but it's not the end. You need the pedagogy, you need the knowledge, you need the science, but you can use your iPhone to teach, to make experiments, to do everything. And that's the technology, not it's the way through. So let's now start talking about some physics. I'm going to inform. I'm not going to go into any detail, but you can ask details or we can talk later. I don't want to be very, to have you very tired, but just give you information, and even if it's not in your field of knowledge, you should gather the main information. So let's start with nonlinear optics in 2D materials. These are some work that we did using what we call meta-surface. So in this part here, there's the pointer here. So in this part here, you see a meta-surface that was prepared by self-assembly. It was prepared at the Naval Research Lab. They put some material here, they shake these. There is a microscope slide inside this vial, and then you have this material coming and sticking on the microscope slide. You see those two peaks here. One is by transmission and the other one is by reflection. The color is different. And then what you have there is these are those gold, well-organized gold pattern. And this is about 25 nanometer in extension and then about 15 nanometer in height. And they are well-organized. And good thing is you can control the distance between them by the number of carbon that you put here in this material. So what we do is we characterize the optical nonlinearities. So what's an optical nonlinearity? When you have a beam of light with certain intensity, even in this glass here, if you go through weak intensity, pointer, laser point, it goes through, nothing happens. But if you have a very intense beam, like we saw the femtosecond laser, that interaction of this piece of glass, or even in air with the light, makes it become nonlinear. So the response is no longer proportional to the field, it's proportional to the field to square, to the third power, and so on and so forth. So that we explain like expansion. So this is the polarization response of the medium, which is proportional to the field that's inducing this interaction. So that proportionality is called optical susceptibility. And then we have this so-called Chi1, Chi2, Chi3, and so on and so forth. So what we do is we mainly work with Chi3. These are materials that are symmetric. So Chi2 is 0 there because then minus and plus doesn't matter. So what we do is we look at linear and third order nonlinear optical properties of all those materials. So this is one of, so we have this published, this is a review paper on this particular subject. So now I'm going to go into a little more details in those materials. These are more recent materials. After the graphene, people started to realize that you can have more than graphene. So these are so-called transition metal dichalcogenides. So you have here molybdenum, and you have the sulfide. They get together, and then you can have the whole family. I'll show you. I think I have another view graph for that. And we did a lot of experiments on that. Yeah. So these materials. They are part of group 4, group 5, and so on. So you can get one of the materials together with the other. What's good about this is in the bulk form, they have some property, but when they are in this format, in this 2D form, what happens is it can be semiconducting, they can be metals or semi-metals. So, but just because of the size, and they have a lot of applications already. So this is some more details. For instance, one more important thing, they can go from direct gap to indirect gap or the other way around. And then you can do application. Graphene is very good, but graphene is always conducting. It cannot, many applications you cannot do with graphene, you can do with this material. So for instance, it goes from energy prospect, energy production, piezoelectric device, photonic device, biosensors, everything using those dichalcogenide materials. So how are they made? Different exfoliation techniques. So once you have them, this is one technique that the guys at the Air Force developed by redox production and oxidation. So what they have is they have those flakes with about 4 nanometer in height, and the flakes can be like 100 to 150 nanometer in extension. So you can have those on a film, or you can have them in suspension. So I'm working more in suspension. This is how they prepared it. So they have this kind of route. They have oxidation, this metal oxide precursors formation, and then they go through all these. They have the exfoliation, and at the end of the day, you have those flakes, as I showed in the former picture. These are the papers where they describe the whole process. So they prepared everything. So the whole periodical table, and I have those available. So then it's just, as I said, just having the data, analyzing, and having the people to work. So the main thing we do, the main technique is very simple. It's called Z-scan. You have a laser that you can change the intensity. So you control the intensity here, you focus on your sample, and your sample can move along the Z direction. And then you put a detector here, another detector. One detector, you take the full beam. If you take the full beam, when you have the intensity changing, so if you have a linear regime, light goes through, nothing happens. But if you have a very high intensity, the beam can be either absorbed due to the intensity or can be even more transmitted due to the intensity. So this is the nonlinear part. And by looking at this data, you immediately know the sign, and you can also calculate the value of the nonlinearity, which is here is called alpha 2. In this detector, what you do is you put a small amplitude at the center. What goes through this small amplitude gives you this is the nonlinear absorption, this is the nonlinear refraction. So what goes through here, it can go up and down. So because it acts like a lens that either focus or defocus, depending if you are before the beam focus or afterwards. So what we did then, we look at all those materials. So this is the typical signature. This is tungstenium disulfide. This is molybdenum disulfide. They are the semiconducting. They are most well-studied materials. So here you can see the lines, and the dots are the experiment. The line is the theory, which is known. And this is how you measure this transmission. Some equations, doesn't matter. So what you do is you measure this delta T, and with those equations, you calculate the N2, and then you can see that changing the intensity, this delta T is constant. That means you only have third order nonlinearity, but in this case, it's like linear. So that means there is a high order effect coming in. So you know how to interpret that, and then at the end, what we take are those numbers. So if you want to make some device, optical switching device, you need this number, N2. In this case, we also have it N4. And whereas for the tungsten disulfide, we only have N2. So we did this for all the materials. This is a semi-metallic material. And then the people from theory do all this functional the theory to show, to explain what's going on. And then third order nonlinear refraction is the dominant nonlinearity. Here is for niobium disulfide. We can see interesting feature. The sign of the nonlinearity change as we increase the intensity. So this is a kind of novel. We understood this and we explained. And then we need to do something. When you are working with nonlinear objects, you have to make sure that you know what's the process behind the nonlinearity. And the time response is very important. So here we are in the femtosecond regime. And then there's this technique called optical care gate. Basically, you have two beams that cross the sample here, and you put two polarizers, and then one beam is very strong. It induces a change in polarization, and you probe on the other port. So as you rotate the polarization, it returns. So you have a pulse, it rotates, the pulse switches off, it comes back. So this is the CS2, carbon disulfide, well-known material. It has a two response. This is very well understood. If this is quartz, quartz is purely electronic, so that is a way to measure the laser pulse. So now we have our material. So our material is in this solvent called acetonitrile. And then acetonitrile, it has a slow response, but when you have the niobium disulfide mixed there, the suspension, you see that the response is very fast. So that means first, all the response is coming from here, otherwise you'd see this tail. And then it's much higher. This is, of course, normalized. And then it follows the laser. That means it's purely electronic. So with this set of data, we can understand what's going on. Now, suppose I will use a CW laser, not a femtosecond laser. What do you see? You don't see, or even if you use a very high repetition laser, rate laser, like 100 megahertz, the system, the same system, sees another response. It sees thermal response. So this is called, this thermal response induces a set of rings. So this setup, we use different lasers. So the beam comes here. This is the sample. You can see you can see this figure here where you see this round circle, but here it's not round. There is not a problem, but there is an issue here is that if you are doing this in the horizontal, gravity affects your data. So the rings, they are not circular, they are elliptical because of the effect of gravity. And of course, the viscosity of the medium. So the guys that understood that first say, okay, let's put the sample this way and that's pump up. So in that case, what you see is a very nice round number of rings. And you start with your spot like this. I need to go back here. Go how to get rid of this. What did I do? Okay, no. I need to take out this laser pointer. Okay, yeah. So here is the beam at very low intensity going through the sample. And then if you start to increase the intensity, that's what you see. Right? As you increase the intensity, you are growing. Now, yesterday, okay, see this? Yesterday, I visited one of the labs. I told you to come. So I can't see that on the camera, but they have some way to collect this data. So I told them, set up your experiment. I'll come back in November, and then we do this experiment. And here we put your system, and then we can know what was here. Because here, okay, here is nice. I can count a lot, and I can once you count, what you have is the following. So you count the number of rings as a function of intensity, and then what you have a little equation, and from this equation, you can calculate the value of N2. Now, I did not call your attention, but before the number of, the order of magnitude here was 10 to minus 16, because it was electronic. This is very small nonlinearity. Whereas here you have 10 to minus 6 because it's thermal, it's slow. Because it's low, the nonlinearity is order of magnitude higher. So sometimes people make mistakes. So they measure this and they say, okay, this is electronic because I'm using femtosecond pulse, high repetition rate. That's not true. So one has to be careful, but this is an easy experiment to do. So let's move on. How's my time? What time? What? Okay. 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 Let's move on to imaging and photoacoustics. So imaging is a very important way to understand, to see things. Lots of applications. If you go to any ophthalmologist or many diagnostics, you need this imaging, MRI or wherever. So this setup, this view graph here shows you the main aspects of doing imaging. One is the spatial resolution, right? You want to have a resolution that you can see small things within your body or in the cell that you study or wherever you are studying. The other thing is the penetration depth. You want an imaging that can penetrate as much as possible. And then you want to have molecular sensitivity. You want to know what is there. So it's not easy to have it all together in one kind of technique. So what you do, you normally go multimodality. So that's why you go to a doctor, he asks for magnetic resonance, tomography, X-ray, 3 different things because he or she has different information. So here I'm going to work mainly, I don't know if, no, I did not. So back. So I'm going to work mainly with photoacoustics and OCT, those two here. You see, they can have spatial resolution all the way down to even submicron. They can penetrate up to centimeters, and then they don't have much molecular sensitivity. If you really want molecular sensitivity, Raman is the technique, right? So normally you have to combine these. So what's called optical coherence tomography? It's like an ultrasound, only instead of sending sound and having the sound back, you use light, right? So you have to detect that light, and I'll show you how. We apply this mainly for dentistry, but the first application is in ophthalmology. So these are some of our results. I'm going to show you. Actually, it's here. So basically, you have a microscope interferometer as the base of optical coherence tomography. And then from that, you collect the light, you go to the computer, and you can have what is called the A scan, B scan, or C scan. You can do 1D, 2D, or 3D imaging, basically real time. So nowadays you can build your own, but you can also buy this commercially. It used to be very expensive, like $50 US, 50,000 US dollars. Now you can buy equivalent for 10, 12,000 US dollars, but you can build your own for half of this price. So this is one of the first studies we did using nanoparticles. We wanted to see, this is our tooth. We know this part at the crown, we have the enamel, we have the dentin, and there are the so-called tubules. So to see the tubules, you have to take enamel, dentin, you have to go to if you want to study this. So we wanted to see if we can have if we could see this tubule using optical coherence tomography. And to do that, we could not see, but if we put gold nanoparticles inside, we could see the gold nanoparticles. We could see this due to the scattering of the nanoparticles. So that was done with Paras Prasad. So he knew how to prepare in situ the gold nanoparticles. And that was done together with dental materials that we use to fill in your tooth. And then when you illuminate with that UV light that used to photopolymerize, then you develop the nanoparticles. So that part was known, but have never been applied to within a tooth. So this is the MEV or scanning electron microscopy for this. You can see the nanoparticles. And then the OCT is this picture here. So what's that picture? This is the part of the, this is the air outside here. So this is the interface with the dentin, and this is the tubule. So there is no other picture to compare, because without the nanoparticle, we don't see. So the referee said, well, you compare with what? I said, okay, I compare with this one, MEV. But the difference is that this can be done in vivo. I'll show you that we can use already. So that was one of the experiments. But this is the one I like most because it goes from the lab to the clinic. So when you go for periodontal exam, your gingiva, the doctor put this thing on your gingiva. It pain, it hurts. And if you have the problem, there's this so-called pocket. This pocket should not be deeper than about 3 millimeters, right? Otherwise, you can have food in there, and then you start bleeding when you brush for this, and so on and so forth. So what we designed was let's look at light, and look at the whole structure of the tooth around the gingiva, and then we can measure with micrometer resolution all the distance in there. So we did this all structural study. First, we did in a pig. We evaluated the whole structure. So this is a microscope photograph on the right here. And this is the optical coherence tomography. So on the microscope, you can see all the features here, the same here. And we can measure this gap here. See this gap? That's the so-called pocket. And we can also see this dental calculus that if you don't take care, then you have to make this come off. It's again hurt. So first we showed that we can see everything. Then we did this for healthy people. So that was already in the clinic. We set this up in a clinic, and then we had about 20 people to come, and then we measure this with OCT. That's the pocket depth, less than a millimeter, and then we compare with the normal probe, which is higher than a millimeter. Why? Because you have to feel it. So you go a little deeper without being necessary. So this is after what we did. We cannot induce the disease, but we can treat. So we treat the dentists, the doctors, they treated the disease in many people, like, I don't know, 30 or 50. And then after several months, they come back. So this on the left is a healthy tooth, and on the right is unhealthy. So you see the unhealthy is, this is again, this is the tooth, this is the gingiva. You see this here. So it comes back, it recovers, and then person goes back home. If they don't do the proper prophylaxis, cleaning and everything, within a few months, everything comes back. So that was the main message that we kind of convey here. So what about photoacoustics? So OCT is purely only light. Photoacoustics is a very interesting technique because you send light in some material. If this material absorbs, that light, that material can emit sound. So what we did was, that's how it works. You have absorption of the light. You can have the relaxation, and that relaxation can go into heat. If you have a pulse, that heat expands and comes back, and then it generates this acoustic wave, which you can use a acoustic detector to detect it. So if you watch some movies, you have a laser at the wall, right? And then you can hear what the guy is saying behind the wall. Just watch James Bond movies, very nice. So you can hear why, because I'm talking here, my acoustic waves are going, they're going talking to that wall. The wall is vibrating, and then the light can sense that vibration and then collect. And then I'm doing this here with the microphone, but I could have light and then the microphone afterwards, and so on and so forth. So this is known. So what we did, we set this up, as I said, this guy Abhishek, we set this up. So we have the light coming here. That's our sample. We did all kind of samples. We have this kind of review paper. This is some nanomaterials. They absorb quite a lot. These are titanium nitride. They absorb quite a lot. This is different concentration, and this is without the nanomaterial, so you don't see anything. Same vial, everything here. So this is a tooth. We can see caries. So this is a tooth with caries, just to prove the concept. This is the image we see. And the important thing is we can go down to about 4 millimeters. So we can go deep in the tooth, like 4 millimeters, and still see what's inside, right? So this is one application. There are many applications. We can do a tomography. So we can do this and reconstruct. That's the titanium nitride again, and that's the titanium nitride underneath 2 centimeters of chicken fat. So that means we can go through 2 centimeters of tissue and still see what's in there. You need to be, the light needs to be absorbed. It can be endogenous absorber or can be exogenous absorber. So we can see blood, you can see everything. So you can also do functional, you can see movement with this technique. Okay, so that was again another example. So to end this lots of information, let's talk about the random lasers. This is very, I went to my postdoc in 1902, and this is where I started all this thing and became a field on its own. So I'm very glad to have a lot of contribution on this. So you all know what's a laser. Many of you here use a laser. That box, for you, it needs to be a black box, but you need to know what's inside, minimally, right? Otherwise, you are just cranking a knob. You need to know what you're doing when you crank that knob, because then you know, oh, it's not working, what's going on? Someone touched the mirror, it misaligned, because there is a cavity. There's an amplifying material, there's a cavity here, 2 mirrors. Those mirrors need to be properly aligned, that the light goes back and forward here to give you, laser means light amplification by stimulated emission of radiation. So the stimulated emission is here. When you pump, you amplify, but you need something else. You need oscillation. So in fact, a laser is an oscillator. The name should be laser oscillator by stimulated emission of radiation. You know what it would be called? Loser. And then they said, no way we can call this a loser. Let's keep the amplification. But it needs this key ingredient for a laser is the feedback. So if you take the mirror, you don't have any laser because you do not have feedback. But back in the 60s, 67, Vladimir Letakov, a Russian guy, he said, okay, you don't need to have mirrors to have feedback. You can have scattering material. And scattering materials all over. So he had this theoretical paper, a couple of papers, 91, 92, a random laser. He did not call a random laser. That came after our work. A random laser is a laser whose cavity, it has a kind of cavity, is not formed by reflection of regular mirrors. Optical feedback comes from light scattering in a disordered medium. Can be your skin. Your skin is disordered. So you can have any kind of thing that's a disordered medium, it's a gain medium together. You can have a dye. You can have a dye inside scattering. You can have scattered like zinc oxide or semiconductor material. You can have scatters plus the gain particles. You can do this with dyes, with dielectric nanoparticles or metal. You can exploit plasmonics, anything you think. So we have done colloids, powders, membranes, made chips, and then also random fiber lasers. So this is Letakov's paper. This is a theoretical milestone back in 1968, this publication. Then in 1994, we published this experiment. It's the first kind of milestone paper. The main results is shown here. So this is a cuvette. You don't have, you pump like this, 45 degrees. There's no feedback from the walls or nothing. So this figure here is the spontaneous emission and after the threshold. So you have a threshold. You put nanoparticles inside, and then you have a narrowing. You see that line here is just amplified spontaneous emission. Whereas when you have the nanoparticles, you have a very strong reduction in the line weights. That's a signature of laser. And also here you have the threshold, and then it goes up very quickly. That's how it works. It's very easy to set up a random laser. So if you look here, it's going to be collapsed as I increase the power. This is my hand. I go to the lab sometimes just to make the movie. And then that's how we do the study. So everything comes in almost real time. So another important milestone paper was done by Hui Xiao group, where for the first time, you see here, the signature is a smooth curve, right? It's very smooth. Whereas in Shao paper, what she showed was that you can have those spikes. So these are the modes of the laser. So a laser, to be a laser, it has to have optical modes. Doesn't need to have a cavity, but the feedback mechanism generates optical modes. So she showed that optical modes can appear. There is a lot of story behind this. So nowadays we know a lot about the random lasers. We know basically all the techniques, and this part here is very important. To be a laser, coherent emitter, it needs to have a Poissonian statistic for the number of photons, and then it has been shown that this is true. So this is a real laser, because at some point people still debated and so on and so forth, all kinds of experiments. So just to give you an example, we have a powder of neodymium. With this powder of neodymium, we have laser emission at 1 micron. The neodymium was nanoparticles prepared inside nanocrystals. So nanocrystal can generate second amount. So we have here what we call self-second amount generation. Now, when you have second order process, you can have what we call wave mixing. So the pump can mix with the other emission to give yet another wavelength. So we exploited this to have a tunable random laser. So we can tune all the way from 340 up to 400 and something, 50, 80, by changing the excitation wavelength, right? So you said, oh, if you can change these, why you need to go through all this? Because here is in the UV. In the UV, you still need different kinds of laser. And anyway, this is a random laser. This is a powder. So that powder I can put someplace, and then I can pump, and then I can have UV emission. So these are a couple of examples. We then, in 2007, already in Brazil, we demonstrated the first random fiber laser. It was, to do that, we exploited this so-called microstructured fiber. It has a hole that's like few microns and several holes. So inside this, we put our colloid, and we showed that you can have random fiber laser emission. As you increase the pump power, you see it comes from this width, becomes shorter, and then you can see the narrowing, and then again the threshold. So this was demonstration work. The really good piece of work came after our work, because instead of using this chord field random fiber laser, which is very complicated to work with, people from Raman Kashyap made a random fiber laser based on a fiber back grating. Now, you know what a fiber back grating is. You can write directly in the core of the fiber a grating. If you put one here, then you have a cavity. So that's how they make a fiber laser. That's why you can buy a laser that's very small. It's a fiber laser generating high power because it has gratings there. Now, if those grates are not periodically separated, if they are randomly separated, you can have a random laser. You can also have a random laser based on the Rayleigh scattering. So here you have powders, and you have Rayleigh scattering that scatters light at the same wavelength that the light goes in. That's what happens when you have snow, and you have the sky, the clouds, and so on. So you need a long fiber. So Rayleigh scattering comes from the fluctuation of the refractive index. So if the grating, the fiber grating, when you write a fiber grating, you are changing the refractive index at the position that you have the light going. So if you do that, if you don't need to do that, and if you use the Rayleigh scattering, if you use the Raman scattering as the gain in your fiber, that's what those people in Turitsin et al. Made. So that's the best way to have a fiber, but I'm going to use the fiber back grating to show you several things. This is a timeline for development of random lasers. There are lots of applications. They can go from cancer diagnosis to imaging, to spectroscopy, to nanoscale sensing, to chemical sensing, and so on. Random fiber lasers can have applications from optical amplification to optical imaging to temperature sensing. If you are interested, this is advertisement for a paper I published last year. It gave a lot of help, a lot of work. That's like 90 pages, over 500 references. It's very updated until June 2021 on Rondoles. You have all kinds of stuff. It is in progress in quantum electronics. So now let me just concentrate, I'm going towards the end, on this complex photonics in random fiber laser. Complexity is something that yesterday we discussed, I saw a lot. Most of you work with cells or related stuff. Very complex systems, very complex. So why we call a random fiber laser a complex photonic system? Because it's an open cavity, it has gain, it has scattering, it has disorder. That are the ingredients for complexity. So what do you have in a cell? You have scattering, you have disorder, you don't have gain, but maybe there are some things there that give you fluorescence. If they give you fluorescence, if you do it properly, you can have gain. So there are similarities. Then here what you have, this is a piece of 30 centimeter fiber, doped with erbium. So erbium is a gain medium. And then there is a grating, disordered grating written here, no mirrors, and then it emits light. I'll show you later how it's done. It emits lights. Come back. Yeah. And then what we do here, the novelty is I got together with people from statistical physics. They know statistical physics. I know optics. So together, what we did was we used this system to study things that perhaps you remember from your undergraduate stuff. So paramagnet materials, spin glass phase. I don't know if you heard. I'll tell you what it is. Levy flights, ferromagnetism. This is more advanced, called flow case states. Extreme events in environments every day now, right? Everything to do with climate and so on. Turbulence. Again, turbulence is another subject you have in airplanes, you have all over. So what we did was using random fiber laser. We got different results, and then we published these just using that piece of fiber. I've never seen a 30 centimeter of fiber so productive. Very nice. And that belonged to Roman Kashyap. He published that paper, his paper on the characterization in 2009. He's a good friend. And once we were having, shot whiskey, so I said, that fiber, can you lend to me? Never returned the fiber. So we did a lot. Let's talk about turbulence. So turbulence is a complex multidisciplinary phenomenon. You can see it in very different places. Stock market, this painting by Van Gogh is called Starry Night. The origin of turbulence basically is the fluctuation of a given parameter. So look at this. This is a canal in Brazil, close to where I live. So people study a lot turbulence, and before turbulence happens in water or in fluid, you can have what is called the laminar flow. So in this canal, what you have is, you see here a laminar flow. This laminar flow changes its velocity because of gravity, and then it becomes turbulent. So there was a fluctuation in the intensity. This is very well known. There's this thing called Reynolds numbers. There's a lot of people that contributed to that, like Komogorov and so on and so forth. So in fluids is the increment of velocity distribution that gives you the turbulence. In photonics is the increment distribution of intensity of the light. So I'm not looking at the average. I'm looking how the light increments, the intensity jumps from one point to the other, and I look at this difference. So there are lots of equations, and then basically, if you have a well-behaved system, then it's Gaussian. If you go to the turbulent regime, it's non-Gaussian. That's the main thing. Of course, there is a lot behind it. I'm not going to detail. It has been shown before in fiber laser in one-dimensional system. So what we showed this for the first time in the random fiber laser a few years ago. What we do, we look at the spectrum. So like yesterday, many students showed spectra for absorption, for fluorescence. You see lots of spectrum like this. Normally, we look at the intensity, and then we look at the average. So there's an average here. When we are near the threshold of the laser, see how intensity behaves. And then above threshold, it's again okay. So it's lasing here, but it's not as well behaved as here. So now what we do, we don't look at average. We look at the distribution of intensity fluctuation. Then comes the equation. If you use the proper equations, which what you have, this is something complicated. I don't know anything about this. So dots are the experiments, and line is the application of this equation. And you see, this is a Gaussian behavior. This is plotted on a log scale. So you see this kind of picture. And you see this behavior here. It has this so-called heavy tail. So it's like this triangular shape. This is because it's a non-Gaussian. So it's more exponential like. It has this so-called heavy tail. So this is a characteristic of turbulent regime. So this is all nice. And then another experiment. Right? Forget about turbulence. It is there, understood, published. Nobody complains. So what are spin glass? You know what's a glass? And you know that a glass, this glass is here, it's solid because we are at room temperature. If we heat it, and maybe with the heat that is coming here, glass can melt. It's actually a fluid. So, and the SiO2 in there, now it's frozen, right? But it can be all loose. So spin glass is a term that comes from this, but applied to magnetism. So you have spins in your, so you have your atom, you have spins. If you only look at the spins, if they are all ordered, you can have what's called ferromagnetism. If they are one up, one down, you have antiferromagnetism. Now, what happens if you say, okay, now I want one up, one down, I want to put another one here. Those two, if this one is up, those two can be ferromagnetic, those two can be antiferro, but if you put this here, what happens? You have a problem. This problem called frustration. You frustrate your system. So that you have this kind of a chain or net where you have this kind of thing that you don't know whether it's not antiferromagnetic, it's not ferromagnetic, it's called the spin glass, right? Spin glass phase. So you can have a paramagnetic here with disorder, but no frustration. You can have spin glass, disordered and frustration. So how you come from one to the other, you change temperature of your material. So there is a critical temperature, below that or above, you have different phase. So this is all well known, well studied. This is that's a cartoon to show paramagnetism, and spin glass, it's all frozen. That's the main difference, different temperatures. So people, since the 70s, have been studying this in magnetism. So names like Maidosh, Edward, and P.W. Anderson, the same P.W. Anderson localization. And then Sherrington, Keith Pratt, all those names for people in magnetism, they have studied that. But in the late 70s, this guy, Giorgio Parisi, he explained that phenomenon. And to explain that phenomenon, and he's the guy that won the Nobel Prize last year, one of the guys. To explain that phenomenon, he invented this thing called replica symmetry breaking. So what he did, he said, okay, I'm going to describe how two spins in a given state, they evolve to be in a different state. So he introduced this so-called Paris overlap parameter. There is a probability distribution function. If you look at this picture here, you see up, 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 down, up, down. Here is a little bit different. So this is a different replica, and those alpha and beta here are related to those alpha and beta. So there is a lot of theory behind. Everything is well understood. Then what you have to look for is this. If you have a system where you have a replica symmetric, then the probability distribution function is centered at 0. This has to do with the fact that the energy landscape is well behaved. Now, if you go to this regime where you have spin glass, you have many minima. Because you have many minima, what you have there is this, it can be plus or minus 1. So that is the signature that we should look for. The problem is that there, until 2015, there was no experiment in any area of physics to prove that. So this guy, Claudio Conti, he's the same university in Italy, and in 2006 he wrote this theoretical paper talking about glassy behavior of light, right? And then there is an analogy. Analogy is always very good. In the magnetic system, you have the spins and you have the temperature. In the photonic system, you have the modes. Remember I told you random lasers need mode? So the modes behave like the spins, and the pump energy, because when you pump, the energy goes from below threshold to above threshold. So there is a threshold power, critical temperature, right? So same group in 2015, they used a random laser to show the replica symmetry breaking. So this is the result from using the equation, below threshold and above threshold. And then that's what you have for the Paris parameter. It goes from 0 to 1, going through a threshold. So very nice. Now, when I saw these two papers, I had seen the other one before, but when I saw it, I talked to my friends at the department that are working on this and said, look at this. Let's do similar work and show this is universal. So we immediately did a lot of work using different lasers to show that indeed this universal. And then we did the random fiber laser. We showed that it has glassy behavior. After us, many people have shown in different systems. That's how our laser works. So it's a very simple experiment. This is the laser emission. So you see this spectrum here, wide is below threshold, and this very thin here is above threshold. We know where's the threshold. It's well characterized. Okay, good. So what we do, we take a lot of data to do statistics. You need like 2,000 spectra, below, around, above threshold. We do all the math, and then this is what we see, below threshold, above threshold. So nice. So this is glassy behavior in the same random laser that we had seen turbulence, same material. So then those guys won the Nobel Prize for groundbreaking contribution to our understanding of complex systems. Half of the money to Shukuru Manabe and Klaus Hasselmann for physical modeling of Earth's climate. One of them was for these 2 degrees. He showed these few degrees increase. And then the other half to Parisi for the discovery of the interplay between disorder and fluctuation in physical systems from atomic to planetary scale. So you can see their paper. So now stop. And this group of people have this book written in 1998. First name is called Thomas Bohr. Now, you know Niels Bohr for sure. I mean, know his work, right? Perhaps you don't know much about his son called Ag Bohr. He was also Nobel Prize in nuclear physics. And then this little guy here is Thomas Bohr. He's a professor in Denmark. So in that book, this is written. The existence of a connection between fluid dynamics, turbulence, and spin glass is fascinating, although it is still too early to decide whether it can pave the way to a deeper understanding of the intermittence in fully developed turbulence. So they anticipate that they should coexist. So 20 years later, in this paper, I told those guys, look, we have a set of experiments. From that experiment, we can look at 2 different things. There must be an equation that explains both in the given limit. So they did the theory. So one theory is this one. The other one, so for spin glass, you have a theory, well known. For turbulence, you also have a theory. They don't talk to each other. So what they said, they created this photonic Pearson coefficient. Right? So in the proper regime, so all those letters here have some meaning. For this tau equals 0, you can go spin glass regime. For this tau bigger than 1, you can go to the turbulent regime. There are some math to do here. So the theoretician techniques, they know well. So that was interesting. we did not see this for 2,000 points, 95,000. And they said, look, you need lots of points. So that 150,000 data points without having to stop, that was 3 days working, starting Monday morning, ending Wednesday morning. No sleep. Of course, it was not for me, for the students. I was sleeping. So we had 2 students going around because we did not want to have any interference for switching off the laser, switching on, heating. Everything was kind of as steady as possible. Same condition, the best that we could do. So this is, of course, there are not 150,000 here, but this is a sample. And then we apply the equation. So dots are experiments, lines are equation, the equation that we had, and we showed this properly. So nice. That's the paper that's called Scientific Background on the Nobel Prize Physics in 2001. In that paper, it's a nice reading because you learn in general words. In that reading, then there is this part here, the vastness of the landscape of disorder, replicas, spin glass, and frustration. So all those references here, some of them are there. So they go saying, here, importantly, experimental evidence of replica symmetry breaking has been provided in systems with random lasers. So this is go from here, that Claudio Conte's paper. Then this is one of our papers. And then they go on and say, here, there is another. We also show you that you can have frustration. So if you have a system without disorder, but with frustration between interacting laser modes, you can also have that. So this is some work we also did using a conventional laser, right? And then comes the part that I like most. Finally, the nature of the random laser system allows for the concomitant observation of replica symmetry breaking and connection between the spin glass and turbulence. So 34 is that work, the one I just showed you. So particularly nonlinear wave interaction. Then it comes here to say which link the early work of Hasselmann, one of the Nobel Prize, to that of Parisi. So I didn't know that. I don't have any problem saying I had no idea, but those guys knew, I mean, they realized that, and that opens for us and for the community a good opportunity, because now I can start thinking about using random lasers to study things that are done in the environment, climate. I can do in the lab, like other analogies can be made. So this is kind of very, after many years of work, this is very kind of rewarding. We had this news and views in light science and application. So there's a summary there for what I'm talking about here, the last part. What's next? What's next for random laser? What's next for photoacoustics, for OCT, for everything? For random laser particularly, we have to go into the quantum world, right? Sensing, miniaturization, electrical pumping, all that. Particularly, we need to think out of the box for anything. You know this game. You always lose because you don't do this. Oh, this is cheating. No, this is thinking out of the box. See the analogy. Do not cheat. Think out of the box. It's a different thing. So we'd like to expand our collaboration. I mean, we have equipment all over. There's equipment here. There's equipment in Brazil, all over. We need people. That's the most important equipment. I always say people. So we need to, you have to go there. Not the professor. We come here, we give talk, have a good drink. We don't go to the lab. The students have to go. They go to the lab, and one day I let them go to the beach. That's it. More opportunities for students, postdoc exchange, more multidisciplinary research. This is very important. There's no more focus now. It's multi-focus. Cannot be just one thing. And then, look, what's waiting for you? This is 20 minutes from the lab. So that's where the students will go.
Only there?
No. After 2 papers. 1 month, 2 papers can go 1 day in the beach. Okay. So I'd like to thank you for your attention. We have eyes, even our eyes can laze. This is my granddaughter. She found this, I don't know where, and said, okay, great, let's make it. So thank you very much, and we can have questions.
So, Professor Gomes, thanks a lot for this wonderful display of many applications. I guess if you're worried about talking randomly, so don't get worried because you have random lasers, so you know what can come out of randomness, right? So yeah, it's open for questions. Are there any questions online? Not yet, but any questions from here? I'll start with one.
Yep.
Professor Gomes.
Please.
So the thing is, maybe they will not hear me. The thing is that you talk about random lasers. What about having lasers and we induce randomization in them? In like change phase, change time?
Yes, that's a good question. You can have so I'm going to tell something that we've been discussing in Brazil with two colleagues. If you have a conventional laser, mode lock laser, right? You can have a phase modulator to mode lock, but that modulation normally it's periodic. So if you induce a random phase there, you may have a random laser, even though you have two mirrors. But those two mirrors may not be doing anything anymore. There will be not that will be responsible for the modes. So this is something that it needs to be proved. But you have a good point there. That's a good direction. Because that has to do with the definition, what's a random laser? So a random laser is something that the feedback comes from something random, no matter what. That's the point. And then it generates optical modes, and it has a threshold. And that emission needs to be coherency. Even it can be low coherence. Low coherence is good for imaging. So that's one of the main, perhaps the killer application for random lasers, source for imaging. Right? So, but that's a invite way to verify and to check this. Should work.
And one more thing is, when you talk about random lasers, the type of characteristics apart from modes like transform pulses and so on, do you end up getting the same intensity or same properties in random lasers apart from the randomness, obviously?
Yes, you have the same problems. You can have, depending on your system, you can have kilowatts. I mean, in the power and everything, you don't have good efficiency. But if you have a fiber, right, and then a random fiber laser, you can have any wavelength, if you like. Then you can have, okay, you already have directionality because of the fiber. And by the way, when you have the random laser, all direction that light goes, they are all lazy, right? Different from fluorescence or anything. They all directions, if you look, they are lazy. Another thing, you can have a flexible, right? But you can have all the characteristics, and you can have very high power. Sometimes you need to amplify, but you can have several watts from a random fiber laser at any wavelength.
What is the type of randomness required? Any random arrangement of
And random, yes. We need to do some more studies because there are different types of randomness, right? So, in principle, overall, the main characteristic is the same. Now, it needs to be seen if you have a different kind of, if you have, say, several clusters, how it behaves. If you have a quasi-periodic, there are different types. So, overall, you need some sort of randomness. Can it be first in the fiber? There's nothing loose in the fibers, right? Unless it's like we did first. But it's an conventional, it's the fluctuation of the refractive index that's disorder that makes the feedback. So, but you can, if you have a dye, there are dyes that are not cancerous, right? If you paint dye here in your skin and you pump, emission is visible. So that's why you can use this for cancer diagnosis. If you have skin cancer, the scattering, the cancerous region, is different from the normal skin. So that's how people.
So the scattering is all, it is an interference.
It's an interference, but the good thing is you cannot normally do not control if it's disorder, right? But because you have gain and you overcome the loss, the positive interference wins over the negative one. So if you don't have that, then that's no laser.
So I need to ask one question. What you said, you can follow the thin glass behavior using optical structure.
Yes.
For
Yes. So we have the analogy. Our system, our system has the equivalent of the parameters in a magnetic system that we can study what would be magnetic effects like spin glass in photonics. That's the main thing.
Question was the gold nanoparticle in your dental polymerize in situ, right?
Yes.
Particles. What is it? Are you using surface plasma? Why do you need the gold particle like this?
The gold particle could be another particle. The gold particle is because it's biocompatible. If anything, if anything would be really come out of this from application point of view, one question is, you use nanoparticles that are not useful for bio. So gold, you remember, there's many people wear gold in tools, and so that's why we did gold, mainly for biocompatibility. But there are other scatters that could be used.
The light has to penetrate there.
Yes. Yes. So in that case, what we did, the idea is the following. So if you want to know when you do some treatment, so that's what we call niche applications. So for some treatment, you need to already open your teeth, which you can do with laser. And then you need to assess that region of the dentin or the tubule. Now, then you assess, and so what? You have nothing to see, right? So typically, what the dentist has to do some work is the access, clean, and then filling. So if you want to do it more elaborated, you assess, you feel what's going on, or nothing. Then okay, close or clean more. That's the idea. This is kind of very futuristic work from the application point of view.
So, based on this random data again, and you showed one case where Paris was generating in situ nanoparticles.
Yes.
So, if you would generate in situ nanoparticles, say tumor cells and all those things, you can actually have a random data out there.
If there is a gain medium there, yes.
Well, gain medium would be a nanoparticles.
Well, if you have a rare earth nanopart versus neodymium, whatever, yes.
Okay, we can
drop
it for lunch. No
But typically, when you have this, what is the concentration?
Okay.
Oh, you need to find the right
Yeah,
concentration, because if it is
So,
too low, then you don't have
to your
enough gain.
office, or
If it's too high, you can have quenching. So you basically you can calculate, you can estimate before you do.
But do you have to worry about AC, amplified spontaneous?
Yes, you have to be very careful. You have to know how to differentiate that you are not looking to ASE. So ASE has a kind of flow, and it can be very tricky. So the laser really has a kink, whereas the ASE goes smooth. Other characteristics of ASE are very similar to random laser, except for the coherence aspect. But many characteristics are very, very similar. Also, the reduction in bandwidth is much stronger for a laser than for ASE. Yeah. But ASE is, at the beginning, many people said, no, this is ASE. You have to prove it also.
I will see you later.
Okay, yes, sure.
Any questions? Yeah.
So, is there any size threshold for the scatterers in random lasing?
Yes, you have to, if you have that's right, before our work in 94, there are maybe 3 or 4 papers using neodymium powders. They said, oh, we see stimulated emission. The problem was the powder was big enough, like few microns, that you can have what's called whispering gallery modes. So if the particle is too big, then you can have this effect. So you have to avoid. And if it is too small, you may be able to use it, but it depends on the regime that you are for the scattering for your wavelength. So there is a range, a big range. We have done with 50 nanometers all the way to just submicron.
So, for example, like if you have these protein aggregates in cells, different oligomers and different sizes, so can this lasing give an idea?
Yes,
Like,
yes. For instance, our skin, right? I mean, our skin is scatters light. So as I said, if I put dye here, the skin, the size of the scattering material in our skin is enough to make it laser. So I know there are lasers based on cells using GFP and things like this. I don't know of any cell-based random laser, but it's possible. I have discussed this before with this guy in China, Shenzhen, but we never did it. So that's something that can be feasible. Yes, I mean it would be just one of those things, a publication, and so, but someone clever will use that for something. Okay. Well, it's in the megahertz regime. So you can have megahertz detectors. You can detect that very easily. Yeah. And the main thing is that you need is to have an absorber. So if you absorb light heavily, so if you have a material that you look at the spectrum, the absorption is at say 400 nanometer. If you put 100 nanometer light there, you can have this emission. Normally, so you need post light, right, to start with. Can be kilohertz, can be few hertz, and the wavelength has to match the peak absorption of your material. If you have that, then the proper detector, ultrasound detector, you should be able to see it. There is a paper in Ops and Photonics News as a review on this, very, very nice, showing very broad without going into many details. Yes. Okay, nice question. So you need a material that can absorb. So for the random laser, you have the two ingredients for the material. It needs to have a gain, right? And then the material can have gain, and it can be a powder that scatters itself, or you need a scatter outside. So you say, okay, I want the material to be itself the scatterer. So then think about zinc oxide. Zinc oxide, the powder of zinc oxide, 200 nanometer size, it emits in the UV. If you say, okay, I want neodymium, I want erbium, so, or I want something that I go together with a dye, or I can have a polymer. So, but the main thing is the material, you need gain and scattering in the same or two different materials. That's the main thing. No. Yes, no. You excite the material, right? And that material generates the sound waves. So the laser only excites. In that case, the light, the sound wave is not carried with the light, right? So the light comes, strikes the material, and the material generates the sound waves. So you detect the sound waves separated. You can do experiments where you kind of encode the sound waves in the light. That's a little different, right? So, but for what you are asking for what I'm doing here for imaging, you use the light. So you pulse, you switch off your pulse, then the sound comes out. And then next comes, and so on and so forth. Yes, to separate process. If you don't have an absorption, then you don't generate. You need the light to be absorbed. Yes, but yeah, well, once the light is absorbed, then sound waves generated, then it propagates. no problem. Oh, if there is, no, of course you need the medium. I mean, yeah, you need the medium because sound needs a medium. If you have vacuum, for instance, then you need a medium. In fact, our experiments are done within water because water is better than air for transmitting ultrasound. So between the sample and the detector, we have this always in water. If you look at the experiments that people do nowadays, they normally have a big chamber because they need to rotate things and so on and so forth because it's filled with water. So if you can use ultrasound to look at a mouse brain, right? So what they do is they put the brain from underneath within a kind of plastic bag. So because you cannot rotate the rat, you rotate the thing inside. So it's a big setup. One of the clever things that Avishek did was we had the thing. In our case, we had a tooth. We could put it to the water. We had it here, but instead of rotating the whole thing, so he said, "Oh, let's put a ball bearing underneath, magnetic ball bearing, and then the sample was on a magnetic stand, and that rotated magnetically." I mean, our system is very small, a small thing, but it's great. So we can do this very easily now, right? So, and that is in water. So if you had vacuum between the sound channel, then you don't detect it. If you have air, you can detect, but it's poor. If you could have even another, when you go to make ultrasound, they have this gel to make the matching between your skin and the detector. So you need a matching fluid. So we use water, but could even be a better one. But you're right. For ultrasound propagate, you need a medium. No, not in this way. So no, in this case, the laser is only to excite. We achieve very good penetrations. You can achieve centimeters. Yeah, and resolution can be micron, depend on there is always compromise between resolution and penetration depth. But you can have micron. You need to have a good high frequency detector, right? And mainly these, and then the penetration then can be less, but you have higher resolution. So if you want to start cells, for instance, or very small things, you don't need that penetration. So you can have less penetration, but you can have higher resolution. Whereas for OCT, for instance, you can never ever have more than a few centimeters because it's only light. More? Thank you. Thank you. Fantastic. Thank you all for coming. Thank you for the